Hey folks, today we're going to continue graphing rational functions, and we're going to go a little bit more in depth on graphing rational functions with our different asymptotes, and we're also going to determine a few more function characteristics along the way for this. So let's get started. So we have a rational function f of x, and it's made up of a polynomial over a polynomial. So our polynomial in the numerator is p of x, and we're going to say that p of x has a degree equal to m. So it has a degree of m. And q of x, we'll say, has a degree of n. Okay? So, for example, you could have a quadratic over a linear. You could have a cubic over a quadratic and such. So there are three possibilities that relate our degrees. Okay? We could have it so that m is less than n. So in that case, the degree of the bottom is bigger than the degree of the top. We could have it that m is equal to n, in which case they are both the same degree. So I could have like a quadratic over a quadratic. Or the last case is that m could be greater than n, in which case the degree of the top is bigger than the degree of the bottom. So these are the three different cases that we have to graph, and this is what we have to keep in mind when we're analyzing our function to determine how we're going to approach this and how we're going to graph it. So we're going to look at graphs that have each of these three cases. So let's get started. So the first case we're going to look at is m is less than n. And it has a horizontal asymptote at y equals 0. The vertical asymptotes are when q of x is equal to 0. And the x-intercepts are when p of x is equal to 0. So let's talk about why each one of these would be the case. Why does this have a horizontal asymptote at y equals 0? If you recall last time, horizontal asymptotes describe our end behavior of our graph. So if we think about it, as x is getting bigger, since the degree of the bottom is larger, your denominator is getting bigger much faster than your numerator. Because if you plug in 10, the numerator would just be 10, and then the denominator would be 10 squared, 100, so it would be 100 minus 16, so it would be 84. And so as x gets bigger, our denominator is going to get much quicker, so it's going to be, our graph is going to get drawn down to 0, because the bottom is going to become really large, while the numerator stays smaller. So it's going to get drawn down to 0. So that's why the horizontal asymptote is at 0. Now our vertical asymptote is when we have discontinuities, and so that's when is our denominator going to equal 0? Well, to figure that out, we have to do a couple things. We have to factor our function. So we have x over, well, this is the difference of squares, so this is x minus 4 and x plus 4. So when would this equal 0? Is that plus or minus 4? And that would be my vertical asymptotes. Now the x-intercepts, just like we talked about last class, when we're doing these, all you have to do to find the x-intercepts is just set your numerator equal to 0, and that will find your x-intercepts. So let's get started graphing this. We'll figure out how much we can, then we'll take a look at it on the calculator to see if we've done a pretty good job. So the first part, we know that our horizontal asymptote, since the degree of the bottom is bigger, is at y is equal to 0, because it's getting pulled down to 0. Our vertical asymptotes, okay, are going to occur at x is equal to 4 and x is equal to negative 4, because that's where our denominator is equal to 0. So the first thing I like to do is put in my asymptotes, because this sort of forms a guidelines of how our graph is going to look. So at positive 4 and at negative 4 we have vertical asymptotes, and then we have a horizontal asymptote at y is equal to 0. We can also find our x-intercept by setting our numerator equal to 0. Well, if I set p of x equals 0, that's just x. So if I set x is equal to 0, I don't really have to solve anything, so we know our x-intercept is at 0, comma, 0, okay, which also happens to be our y-intercept for the graph. So this is our x-intercept, and I can plot this on here. And while I'm doing this, I can bring up a rule for asymptotes. So you can never cross a vertical asymptote because that means you'd be going into the discontinuity. But you can cross a horizontal asymptote because horizontal asymptotes only describe the end behavior. They don't describe the graph around 0 or right around where we're going to be graphing. They only describe as you go way far out to the right and way far out to the left. So you can cross a horizontal, you just can't cross a vertical. And as you remember last class, you're always drawn to vertical asymptotes, and as you head towards infinity and negative infinity, you're drawn towards horizontal asymptotes. So you have to keep those in mind while we graph. So what I have here is the point 0, 0. This is all I have right now. So to find more points, I need to plug in values for my function. So I need to figure out from 0, 0, am I heading down or am I heading up? What's happening? How am I going to draw towards this vertical asymptote? How am I going to draw towards this vertical asymptote? So what I'm going to do is plug in values for x. So I'm going to plug in f of -1 and f of 1 on here. So if I plug in f of 1, I have 1 over, and then 1 squared minus 16 is -15. So f of 1 is -1/15. So really small. So at 1, it's right there. Okay. And what about f of -1? Let's do that. Okay. So it's -1 over -1 squared is 1 minus 16 is also -15. So it's positive 1/15 right here. Okay. And now I know I have enough information that I can draw my graph like this. And you may be thinking to yourself, well, how do I know it doesn't come back down? Come back down this way. Well, you have to keep in mind that we already know our x-intercepts are at 0, 0. That's the only x-intercept. So we can't, if we were to come back down, we'd cross the x-axis again, and we would create another x-intercept, and we can't do that. So we know since we're above the x-axis, we can never go back down, so we know it has to go up. Likewise, when we're below it, we know we can't go back up because we already know we only have one x-intercept, so it has to go down. And so our middle part of the graph has to look like that. So now I have my middle section done. I need to figure out what's happening on the right side of x equals 4 and the left side of x equals -4. So I'm going to plug in another value. I'm going to plug in f of 5 to figure something out. Plug that in. If I do that, I have 5 over 25 minus 16 is 9, so it's 5/9. So I'm at 5/9, so I know at 5/9, I'm right in there, a little over half. And then I'll do f of -5. If I do that, I'm at -5/9 over here. And again, this tells me I have enough information that I can graph the rest of this because I know I have to get drawn towards my vertical asymptote. And I have to get drawn towards my horizontal as I go to infinity. And I know that this couldn't have gone down because I would cross the x-axis again and create another x-intercept, which we don't have. Likewise over here, I know this is going to draw towards my horizontal, and it's going to draw towards my vertical. So that's the information that I have. Let's see if we match this up pretty good. So I put it in the calculator, and we do that, and there is our picture. It's not too bad. You can see where our asymptotes were at +4, -4. You can see how I put it in the calculator. You have to make sure the denominator is in the calculator. And there we go. So that is our first example. Let's take a look at another one with the same situation. M is less than n, so our degree of the bottom is bigger. So we know that we have a horizontal asymptote at 0, so we can get started on that. Okay, vertical asymptotes occur when q of x is equal to 0. Well, q of x is our denominator, and this is x squared plus 1. Well, that's the sum of squares, and we know it has no real solution because I can't plug any value into x and get this to equal 0. So this has no vertical asymptotes. So our horizontal asymptote is that y is equal to 0. Our vertical asymptote, well, there are none, because we can't get our denominator is equal to 0. How about our x-intercepts? X-intercepts occur when p of x is equal to 0. Well, when can I get this equal to 0? Well, since that's just a constant, I cannot get it equal to 0. So I know our x-intercepts are none, because we can't get 4 equal to 0. So I don't have a lot of information so far on this, so I just need to plug in values. So what I can do, one good point to find always is your y-intercept, because you just need to plug in 0 in for x. If I plug 0 in for x, I have 4 over 1. So my y-intercept is at 0, 4, right here. And that's still 1 point. So let's find a little bit more information. So let's find f of 1. If I plug in 1 here, I have 1 plus 1 is 2. 4 over 2 is 2. So I have the point 1, 2. And let's do f of negative 1. Same thing, if I plug in negative 1 here, I'm going to get 2 also. So it's negative 1, 2. And I can see what's going to happen. If I keep on plugging in larger and larger values for x, my denominator is getting larger and larger while my numerator stays the same. So this fraction is becoming smaller and smaller and is getting dragged down to 0. So I know my graph is going to get dragged down to 0 towards our horizontal asymptote. So it's just a little hill like this. And I know it can never cross the x-axis because we have no x-intercept. That's one big thing, you guys, you have to keep in mind, is the idea of once you find your x-intercepts, you cannot cross the x-axis again. So that's really going to tell you how your graph is going to behave and give you some boundaries of where your curves can be drawn. So our next case is where m is equal to n. And we actually did a little bit of this in our last tutorial. So our horizontal asymptote occurs by looking at our leading coefficients. And we talked about this last time, that all our other stuff becomes insignificant as x gets really, really big. So as x gets really, really big, this negative 4 becomes inconsequential, and it's really just x squared over x squared, which would just be 1 over 1 when we canceled out the x squareds. So you have to look at the leading coefficients of your highest term to find your horizontal asymptote. Your vertical asymptotes and your x-intercepts are found the exact same way otherwise. Vertical asymptotes are when q of x is equal to 0. Okay, so let's get started with this particular graph. So we have y is equal to x squared over x squared minus 4. So the degree of the top is 2, degree of the bottom is also 2. So I know my horizontal asymptote occurs by where and y equals 1, because I would divide my leading coefficient. So 1 over 1 is 1. So horizontal asymptote occurs at y is equal to 1. Where are my x-intercepts going to occur? Well, I need to factor, so I have x squared over x minus 2, x plus 2. And so where are they going to occur? They're going to occur at positive 2 and negative 2. So I can plug those in, and by plug in, I mean graph them. So now I have my framework for my graph, and at y is equal to 1. Okay, so here's the framework for my graph. So now I basically need to find points. Okay, and again, the one we always find is we want to find our x-intercept, because that tells us a lot about where we can and cannot be for our graph. So I need to set my numerator equal to 0. So to find my x-intercepts, I set x squared is equal to 0. Well, so that just means x is equal to 0. So my x-intercept is at 0, 0. So right there. Okay. So that's what I have. So now, since I am on the x-axis, I need to figure out, am I going up or am I going down? Because remember, we can cross horizontals near 0 if need be. But we can't cross our verticals. So I'm going to go up towards the vertical or down towards the vertical, up towards the vertical or down towards the vertical. So we're going to plug in values. So we need to plug in for f of 1 and f of negative 1. So f of 1, if I plugged in, I have 1 squared over 1 squared minus 4, so that's negative 3. So that's negative 1/3. So f of 1 is negative 1/3. F of negative 1, plug it in, 1 over 1 minus 4 again, so it's also negative 1/3. Okay, so that's enough information to tell me what's happening in between these two vertical asymptotes, because I know I can't go up again, because I'd cross the x-axis again, so I have to continue to go down on both sides. So it's going to look like that. Now we need to figure out what's going to happen on the outsides on the outer portions of our graph. Okay, so we need to look to the right of our vertical asymptote at x equals 2, and to the left of our vertical asymptote at x equals negative 2. So I want to figure out what's going to happen at 3. Where's it going to be? Is it going to be in this region or this region? So plug in f of 3, and we're also going to do f of negative 3. And figure out what we have. So f of 3, if you plug it in, ends up being 9/5, and f of negative 3 also ends up being 9/5. So if we plot our points, so 9/5, that's a little bit under 2. So we're going to be right around here and right around here. So I know that I have to get drawn up towards my vertical asymptote, because if I was drawn down, I would cross the x-axis, and I know I can't do that, so I'm drawn up towards it, and I have to end up drawing towards my horizontal. Likewise on this side, I have to draw up, and I have to draw down, or to the right, towards my horizontal as we go on. Okay, so that is that particular graph. We can plug it in the calculator to verify that this is indeed what it would look like. So it's drawn up, and it's not touching the vertical, even though it's getting close. I'm just a bad drawer. So that was bothering me, so I fixed that so it doesn't look like it's crossing. So anyway, onward again. Alright, so now we have this one. So this one we have a quadratic over a quadratic. So the first thing I want to do is, well, I know it's the same, so I know it's going to have a horizontal asymptote. But I want to factor this. I have x squared minus 3x minus 10 over x squared minus 2x minus 5. So if I factor this, this is x minus 5 over x plus 2, and then x minus 5 over x plus 3. Okay. The interesting about this is that one of our domain restrictions gets canceled out, x minus 5, because that's on the top and on the bottom. When this occurs, it creates something called a hole. A hole is also a discontinuity like a vertical asymptote, but instead of being an asymptote, it's just a hole in the graph, and it's a point. So a removable discontinuity is a hole created by a domain restriction that can be canceled out when we simplify, and it's an empty point in our graph. So what we're really going to graph is this part right here. We're going to graph f of x is equal to x plus 2 over x plus 3. That's what we're going to graph. And then we're going to come back and look at what happens at our removable discontinuity. So if we focus on what we have up there, okay, our degree is the same. So our our horizontal asymptote is at y equals 1 because we divide our leading coefficient, so it's at y equals 1. Our vertical asymptote is at x is equal to negative 3. So there's our asymptotes right here. If I want to figure out our x-intercept, well, we just set the top equal to 0, so x plus 2. So x is negative 2, so at negative 2 comma 0 is our x-intercept right here. If I want to figure out our y-intercept, we can just plug in f of 0. If I plug in 0 into top and bottom, I just get 2/3. So it's 2/3 right there. So that's enough information on this side to graph it. Let's figure out on this side, on the left side. So I'm going to plug in for f of negative 4. If I plug in negative 4 into this, negative 4 plus 2 is negative 2. Negative 4 plus 3 is negative 1. So negative 2 over negative 1 is 2. So it's right here. So that's enough information. So I know I have to draw towards this. Can't draw down because I go across the x-axis. I go this way. Okay. And now here, I know it's going to draw this way. And it's going to draw this way. And head towards. But now, we need to think about our removable discontinuity. We know that x cannot equal 5, because that would make this equal to 0. So there's going to be a hole here at 5, and then the graph is just going to keep on going. There's a little blip in the graph that doesn't exist because that was a domain restriction. So there's actually a hole, and you have to draw it as an open circle, and it keeps on going. If you want to figure out what the actual value of the hole is, all you need to do is plug in your discontinuity into your simplified graph. So if I want to figure out what f of 5 is, well, I would just do 5 plus 2 over 5 plus 3, and so I would get 7/8. So for this graph, the hole occurs, the removable discontinuity is at 5/7/8. So this does not occur in this graph. Let's take a look at it on the calculator to see if it shows up. So I've graphed it right here. You can see our graph is pretty good, pretty accurate, and you can see if you look closely right here, there's a little blip where we got 1 pixel missing at x equals 5, and that represents the hole in the graph. Let's see if I can actually zoom in around that, and you can just take a look really quick. Let's zoom in right in there. All right, so there's our graph, going. Oh, bloop. There's the hole right there at 5/7/8. So if I trace right around there, right where I was, see at 5 there's no y value because there is a restriction right there, and then it keeps on going. So that's what a removable discontinuity is. So it's just a domain restriction that can get canceled out when you are simplifying your rational function. So we have one more case to take a look at, so let's do that. So our last case is when m is greater than n. So our degree of our numerator is larger than the degree of the denominator. And this is my favorite case because we don't have any horizontal asymptotes. We have what is called a slant or an oblique asymptote, and we find it using synthetic division. That's right, we're bringing it back. We got to use synthetic division. So, or long division if you want, but we're going to use synthetic division. The rest of everything else is the same. Vertical asymptotes are also when q of x is equal to 0, x-intercepts when p of x is equal to 0. But this is very exciting because we get to reuse something that we learned several months ago. So fun times. All right. So why do we have something called a slant asymptote? Well, if we think about this, as we plug in large numbers, our numerator is getting bigger than our denominator at a much faster rate. Because the top is squared, the bottom is linear. So what that means is that we're not getting dragged down to 0 because the bottom's not getting bigger quicker than the top. The top's getting bigger than the bottom, so we're getting actually dragged to infinity. Okay? What the slant asymptote tells you is how fast you're going to infinity. So it's like how quickly you're going off to infinity. So let's find out some information about this graph. So first thing we want to do, we see that this is going to have a slant, hopefully. So let's start factoring, figure out what this is. So this is x minus 5, x plus 1. Nothing cancels out, so we know it's not going to have a hole. So, first thing we want to find is our vertical asymptote. We know that's going to occur at when our denominator is equal to 0, since nothing cancels out. So that's at x is equal to 2. So that's our vertical asymptote. Okay. So now let's find our slant asymptote. So we find it using synthetic division. Since we're dividing this polynomial by this one, we're going to use synthetic division. So I'm going to set that up over here, and I have, remember, we put our coefficients and our constants, so we have a 1, a negative 4, and a negative 5. And what goes out front? Well, opposite of this, so 2. Bring it down. 1, multiply these two is 2. Add these two together is negative 2. Multiply 2 and negative 2 is negative 4. Add these two together is negative 9. So, if I were to write this out, when I divided x squared minus 4x minus 5 by x minus 2, I got 1, negative 2, negative 9. Well, what does that represent? That represents y is equal to 1x minus 2, and then a remainder of negative 9 over x minus 2, if you recall when we did synthetic division. So now, this represents our slant asymptote. Okay? We don't need to use our remainder. Take that away. Why is that? Well, as x gets really, really big, our remainder is going to become closer and closer to 0 because we don't have a variable in the numerator, and our denominator is just getting larger and larger. So this right here is our slant asymptote. Our slant asymptote for this is at y is equal to just 1x minus 2 or x minus 2. And so I can put x minus 2 in, so we know our y-intercept is negative 2, slope of 1, so it's up 1 over 1, up 1 over 1, like this. And slant asymptotes have the same general behavior as horizontal. You get drawn towards them as you go to infinity. So let's figure out some information for our graph. We have that. We know our vertical was at x is equal to 2. Let's figure out our x-intercepts. Our x-intercepts are when our numerator is equal to 0. So our x-intercepts, since we already factored it, to figure out if we had any removable discontinuities. This is factored, so our x-intercepts are at 5, 0, and at negative 1, 0. So we have 2 in this case. So 5, 0, and negative 1, 0. Okay. let's figure out our y-intercept. Okay, let's plug in 0 in for x. So if I plug in 0 in for x in this, those go away, the x squared goes away, and we really only have our constants at the end. So we have a negative 5 over negative 2 when I plug in 0, so that's 5 over 2. 2.5, so I can go up to 5 over 2. 2.5 right here. Alright, now I say this is enough to graph it. So, what are we going to do? We are going to draw towards our vertical. We know we can't go down because we would cross the x-axis again. We're going to go through this other point, and we know we're going to head towards our slant asymptote. Like that. Okay. We know on this side, we know we're going to draw towards our vertical asymptote. Okay, and draw towards our slant. Okay, so that is that one graphed. Well, I had to redraw that because I was not a fan of drawing it in the same color as my asymptotes. So that's our graph right there. Got a lot of information. So we got one more to look at, and then we'll be done. So for this one, we have x squared plus 3x plus 2 over x plus 3, and I forgot there's no f of x right here, so let's make sure we have an actual function and not just an expression right there. So, degree of the top is bigger than the degree of the bottom, so we know this is going to have a slant asymptote if nothing cancels out. So let's do that. Let's figure out if anything cancels out. Well, this is going to go to x plus 2, x plus 1 over x plus 3. Alright, so nothing cancels out. So we know that. So now we know our vertical asymptote is that x is equal to negative 3. So our denominator is equal to 0. We can find our x-intercepts quickly before we find our slant, because where is our numerator going to be equal to 0? Negative 2 and negative 1. There we go right there. So now let's find our slant asymptote. So I need to do synthetic division. So I'm going to set that up. Okay, we have 1, 3, 2, our coefficients and our constant of our numerator, and then negative 3 out front. Okay, what would make that equal to 0? And so drop down, multiply, add, multiply 0, add 2. So this is going to be y is equal to 1x plus 0, and then plus 2 over x plus 3. And again, this is our remainder, the 2 over x plus 3. And as x gets really, really big, this gets drawn closer and closer to 0, so it becomes insignificant. So this right here is our slant asymptote. And so we can put that in at y is equal to x. So that's y is equal to x, has an x-intercept of 0, 0, slope of 1. So we can do that. So we only have 2 points on here, so I need a bit more to figure out how our graph is going to look. So I need to find our y-intercept. Y-intercept, we just plug in 0 in for x. If I plug 0 in for x, that's 0, this is 0, this is 0. It's just 2 over 3, 0 2/3, so it's right here. Okay. What else do we want to find? So let's find f of negative 4. Let's figure out what's happening on this side, on the left side of our graph. So we'll find f of negative 4. And if I plug in negative 4 into my function, you can do that. You're going to get back out negative 6. So at negative 4, it's going to be at negative 6 right here. So let's see if this is enough. Okay. So I know I'm going to get drawn here towards this. this has to come down, and then it has to go up through it, so that I know it's heading upward, so it has to head towards my vertical that way. Over here on the left side of my vertical asymptote, I know it can't head up because it would cross the x-axis again, so it has to head down towards the vertical asymptote that way, and I need to head towards my slant asymptote as I head towards infinity, so that is that one. So, I know this was a little bit longer. Thank you guys. We'll practice a bunch of this in class. Have a good one.